Okay, so it's a pleasure to again introduce Xinwen Zhu, who will continue with the second talk.
Thank you. So here's the theorem. So basically, I'll first explain an example of this theorem. In fact, this example contains the basic idea of application. So what is it? Well, the very basic idea is contained there. Oh, either one is okay. Hello? Okay, so I'll explain one example of this, very basic example of this theorem, but it contains already the basic idea of applications. So what we are going to do, we are looking at so first of all, there are two things I need to say. First of all, is this on this, because we know the representation category is a tensor category. So there's a natural in the tensor category, in the representation category, there's a natural isomorphism V tensor V, isomorphic to V tensor V. You switch the two vectors. Yeah. So what happens here? Right. So what is V tensor V correspond under this equivalence? It corresponds to this G11 classifying the lattice M2 inside here 1 lambda 0, which is O2. So this is correspond to V tensor V, as I somehow explained before. So therefore, I want to consider an isomorphism, a self-isomorphism of this, automorphism of this object in this category. It's not gonna be the identity map, because we know here it's not identity map. So what it is, by definition, Hom of group 1, group 1, group 1, group 1 is a Q span of irreducible component of the following variety. You have lambda 0, so you consider the this chain classifying one copy, and I have another. Oh, sorry, yes, inclusion direction. I have another chain, and I wanted this to be the same. The ending points are the same. That's a close-up variety inside the group 1 1 times group 1 1. Yeah, it contains two irreducible components. One is given by just the diagonal, namely lambda 1 equals lambda 1 prime. That's going to be the diagonal. So it's a diagonal union of another irreducible component, let's say Z, which you require this, in fact, this is the condition, this lambda 2 is pi times lambda 0. Okay. So it turns out this, as I said, this is not identity map. It turns out this commutativity constraint C correspond to, if I calculate correctly, it's going to be correspond to lambda minus Z. Something like that. Okay, so now here's the idea of how to apply this theorem. So we just consider the following situation. The simple, if I consider point, which is group 0, which is just the lattice, just the standard one. So I consider the Hom from this space to, let's say, group 1 minus 1. Let me remind you, they classify the following chain of lattices. Okay, so there's an inclusion of both are colon 1. So in fact, the Hom space in this situation, you immediately follows from the definition. You want the lambda 2 equals lambda 0. That's a space of that's a subvariety defining the Hom space. So in fact, let me just write it as follows. This is just, you require the condition lambda 1, and lambda 0, lambda 2, and you want this equal. So in fact, this is P1 inside this variety. And in the first lecture, I already explained that this P1, in fact, is -2 curve inside this surface. And now you take this commutativity constraint, you go to -1, 1. What you get is something here. I think you reverse sign and do the same thing. Go -1, 0, go to point. Here, this subvariety, this is a closed subvariety. You require these two isomorphisms. So if you compute, you can compute this homomorphism in two ways. One is inside here. What does it correspond to? It corresponds to, in terms of representation, it goes from the identity goes to the standard representation, turns out the standard the dual of the standard representation. Then you take this is what's called the unit map. You take the commutativity constraint, you get the standard representation, star turns out standard representation, and then go to identity. And we know this is a so it's going to be the homomorphism from the one-dimensional representation to just the vector space C, let's see, Q to Q, let's see. It's going to be given by a number. What is this number? This is given by dimension of a standard representation, which is 2. Okay? But if you go into this business calculated inside here, it basically what it calculates is really calculates the intersection number, something like there's some subtlety of you need to identify this group 1 minus 1 with group 1, 1, applying some commutativity constraint. Let's ignore that, but this is inside the rep GO2, but inside this Satake category, this number is basically the self-intersection. Number of this -2 curve. Just this curve. Okay. So we know it's a -2, but the sign, there's a sign is because there's some side change in the commutativity constraint. Let's ignore that. So, but roughly speaking, the idea in the following application is going to be somehow, if you have this equivalence, then you can calculate certain intersection of some algebraic cycles. You can express the intersection number of algebraic cycles in terms of a representation of a theory of GO2, something like that. So what we're going to do is do it in a more complicated content. So, this is a basic diagram you should keep in mind. So, map C is a commutativity constraint. Yes. I just erase. You can identify group 1 minus 1 with group 1, 1. It's easily. There's some cycle. Yes, some cycle there. I write it here, but. Okay, so now here's what I'm gonna do in a more complicated content. But for this, I need to introduce something which is locally look like this sort of variety, but it's more complicated. For that, I need to let me do some. I guess in the second talk I can use some more fancy, use some more fancy notations and complicated objects. So so I will fix my F is a local field, contains a ring of integers. Let me choose a uniformizer pi, not important. I assume the residual field is, let's see, just FP for simplicity. Okay. So what I'm going to consider is for any R perfect FP algebra, I have the so-called ring of weight vectors WR, and I denote the with coefficient in O as just as follows: WR tensor WK. Oh. So it's let's see if F is FP, this is just the usual WR. But if F is equal characteristic field, this is just the R dot bracket. Okay. So in particular, there's some natural Frobenius would act on here, denoted by sigma. So let me denote dr as spec WOR. One should think this is a family of disks. Parameterized by spec R. Okay. So if I have a E, I just give a notation of like vector bundle on dr, I'll denote sigma E, just its pullback. Along the Frobenius on the. Okay, so definition. So if we fix mu, some sequence +1, -1, -1, +1, just as before, I define what's I call a rank 2 O Stuka on spec R is a chain of lattice of vector bundles on dr, such that dr -1 E1 together with the isomorphism of E0, together with the isomorphism of E0 and Frobenius pullback of ER. Here, dot really means it's an inclusion such that quotient is length 1 if this is 1, and maybe in this direction if it's -1, depending on the inclusion here or here. So if you think about it, if this the last piece, this E0 is a trivial trivial vector bundle, this is exactly the. I mean, you can think if you replace this condition by saying the last piece is a trivial vector bundle, that's our previous variety. This is grow mu. Okay. So this is more complicated, but it's locally. It's just something. If you pick up a trivialized, so let me just write Stuka mu R. Define the moduli space is just the all such Stukas. Spec R. All means the category of such Stukas. So, so maybe before going on, let me just make a few remarks. What are these objects and where do they come from? So, remark 1. So the Stukas are invented by Drinfeld. In global function field cities. as generalizations of elliptic modules. Okay. However, I would see, but the question is there any number field analog? Number field setting. This is unfortunately we don't know at the moment. So in fact, the second thing is what I define is in fact a very special kind of Stukas. In fact, what I define is just what we defined are Stukas with singularities at the closed point of the disk. So in fact, what one can define is more general notion like Stukas with singularity at the generic point of D, or with even with singularities moving along D. With singularities at the generic point of D, or even moving along D. I mean, the last one, I guess, I think there's a definition. Even now, I guess even in mixed characteristic, and this is closely related to the mixed characteristic. This is related to closely related to the so-called the Brurick-Kaysen module. Okay, and what I really want to keep this. Yeah, let me keep this. So, right. So what I just defined, this is there's a multiple modification. What I call this iterated Stukas. If you just consider a very special case, just the mu is just, for example, is just 1. It's just those correspond to E, and embedding of E to sigma E, such that quotient is one-dimensional. It's a locally free sheaf of rank 1 on spec R. Then this is, in fact, according to the result of Gaber, this is the same as p-divisible groups. Of one-dimensional p-divisible groups of height 2 over spec R. So this is somehow, I mean, in this, let's see, this is now F is QP, let's see. QP. So somehow this is I mean, in function field, that's why, like, there's something similar, so that's relations like elliptic module and the Stukas in general. So in over QP, this is a result of Gaber. But so apparently, why you want to introduce such thing if there's equivalence and p-divisible groups are something number theories are very familiar with arithmetic geometry. There are basically two reasons, I think. The first, of course, this is a more linear algebra than p-divisible group. So in some sense, easier. You can even generalize, instead of consider vector bundles on disk, you can consider any G bundles on the disk or something like that. You can generalize to arbitrary reductive group. But the more essential reason is now we have this notion of iterated one, right? If you have this mu, which is it's mu r up to mu 1, so each one is plus or minus 1. So I have this iterated Stuka moduli classifying such chain of bundles on the disk. Such thing doesn't have any analog in terms of Stukas. And there's a very important operation you can play here. If you just start from here, there's a notion of partial Frobenius map. You can, let me denote by sigma nu, denote as mu r minus 1 up to mu 1, then sigma mu r. It's just mu r. Then you have a morphism from this moduli space of Stukas of type mu to the moduli space of Stukas of type sigma mu, namely, which classifying just you require the corresponding modifications is given by this. And this map is, you just send this chain of vector bundles on the disk to the following thing, sigma 1. Okay, to sigma 0, sigma r to sigma minus 1. Okay, so you just, because you can apply pullback of this map along the disk and then put it here. You can continue. So this is called partial Frobenius because if you iterate it r times, it goes back to itself, and that's the Frobenius endomorphism of this moduli space, which, of course, I should say this is not the algebraic variety or algebraic stack, but people can work with it. In various ways, you can make sense of it. There's some technical details, but let me ignore that. Okay, so now the really picture I want to study is the following. So there's a relation of the moduli of Stukas and the varieties I defined, considered before, which is just you can consider moduli of Stukas. If I just trivialize my vector bundle, the end point of this chain, I get something like GL2O tosser, maybe OL, I don't know. Let me write it like that. Just this is the same data as before. Plus the trivialization of E0. Okay. And now this guy could map to my original group mu hat, because now it's really just a chain of lattices. Yeah, and the last one is a trivial one, it's just O2. So in fact, at tau local, they are the same. So it turns out you can, ending the homomorphism, so one can define naturally using this. One can define in this a homomorph map from this Helm space in this category, so 0 to some correspondences between Stuka mu and the Stuka. Okay, just recall this. The homomorphism are given really just some algebraic cycles in the product. So these are locally you can all move to here, give cohomological correspondence here. So I will consider two particular situations. So here's the situation I want to consider. Now, instead of considering just the grow 0, grow 1 as before, I can put Stuka 0. Here I put the Stuka 1 minus 1. Here I put the Stuka 1. Here, Stuka minus 1, 1. It's modular space. Then Stuka 0. Okay, so instead here, of course, this it's gonna be the trivial one, but it's gonna be the sigma pullback along lambda. So here I'm using interchangeably the notation lambda, and I think lattice is vector bundles on the disk. Lattice is a projective rank 2 module on projective O module of rank 2, so I think the rank 2 vector bundles. So here I put partial Frobenius. Okay, so you can consider such correspondence. So then you may guess what would happen here. So here's like sort of you can sort of calculate this cohomological correspondence using the geometric Satake, and this is sort of a meta theorem, which means it's not the actual theorem. It will be correct when you pull back everything to the global situation. Because in the local situation, it won't be correct, but what would happen is you can calculate in terms of, it's going to be just a standard representation times the standard representation times gamma times 1, where gamma is an element in GO2. Okay, so this gamma, in this says it's not a theorem because it doesn't literally make sense. It will make sense later on when I pull back everything to the global in the global situation. But this meta theorem is basically, let me see, a result of Vincent Laforgue. Basically, it's one of his main technical results in his recent proof of Langland's one-direction Langland's correspondence over function field. So, okay, so what I would like consider is another situation. For my application, I will consider another situation. I'll consider the following. So, let me write it in this way. So notation, first of all. So originally, if I have a bunch of representation, let's see W. This is representation of GO2, but because of this signature, maybe I could safely replace this by the, in general, the Langland's do group of G. Okay, so according to the geometric Satake, it gives you some variety, grow W, and also I would like to denote the corresponding version for Stuka as Stuka W. So this is, I mean, basically I'm changing in previous situations, all these are standard representation of the dual of standard representation. And there I use notation 1 minus 1 or so. But now I switch to this because it will be more convenient. Okay, so now let me define the following thing. Construction. we will construct for any, we'll construct a homomorphism from V tensor the V tensor sigma V. Okay. Let me hold. Let me just let me use another notation. So let me give the let me construct the following thing. So first of all, in general, I can consider just using the geometric Satake, I can consider a correspondence between Stukas of type 0 and the V tensor V dual using just the same as the previous one. Construct a correspondence. So locally, you really use a variety of F and Grassmannian, but globally you can switch to the Stuka setting. Then you take the partial Frobenius. So I get here from V star tensor sigma V. Okay, so what is sigma V? Sigma V is a representation of so let me just write it here. In general, if G QP is non-split, then sigma is a Frobenius, but unramified. Let's see. Then sigma would act on the Langlands dual group, and sigma V is the representation of is the twist of V by G hat, where of course G hat is a representation, V is a representation of G hat. Sorry, twist of V by sigma. So in the split case, G is GO2, sigma acts trivially. So we don't have so sigma V is just V. So nothing happens. But in general, you can even do in complete generality. You could, it's partial Frobenius is really a map from the Stuka of type V tensor V star to Stuka of type V star tensor sigma V. So now, you can do, if you have a Hom from V star tensor sigma V to some other representation, let's say W, you can, let's see, for any type A, you construct a correspondence from this to Stuka. Okay. So in other words, what I'm saying is that, in fact, this construction gives us the following thing. So if I have a map from, let's see, Hom of V tensor V star to W of the representation of dual group, I construct a correspondence between two moduli spaces. One is the trivial one, the trivial moduli space of trivial Stukas, and the moduli space of Stuka of type W, just by this composition. Okay. On the other hand, is something interesting is this guy would give us a function from G hat to W, which is a G hat equivariant function. So this is a construction is as follows. So sigma A, I consider its value on an element in dual group is defined as follows. You go 1 to V tensor V star goes to G times sigma tensor 1. In fact, that gives you V sigma tensor V sigma. Use A to W. Okay. So this is in fact, this is a G equivalent map from G hat to W. Here, G hat acts on here by sigma conjugacy. And the G hat acts on W because it's W is a representation of G. Okay, so here's the meta theorem. Okay. Let me denote this by C. This is correspondence. This correspondence A is in fact given by this function. I mean, if you think, okay, it's going to be. Okay, now let me try to make this precise in one particular example, because this is sort of some. I mean, what does it mean to say this correspondence is given by this function? Okay, so in particular, those moduli spaces are really some bad spaces, not the. Don't want to really talk about the cohomological correspondence here. So let me give an example. I mean, I could talk about GO2, but I think maybe it's even simpler to talk about GO3. In fact, unitary group. U3. Let's see some ZP. Non-split, some unitary group. So you just take W to be the wedge of the standard representation. Okay, so what I have this correspondence C of A mapped to Stuka W. Here Stuka 0. But on the other hand, I can globalize this situation. I can pass to globally, I can find the G, which is a unitary group. Let's see, this is GQP. Maybe I want to take similitude group to make everything work. Unitary. Of signature. Let's see, 1, 2, or maybe 2, 1. Associate to some quadratic imaginary. Associate to some, let's see, E over F, quadratic imaginary. So then, after choosing the appropriate level structure, what I want a GQP is just that one, okay? And P is in unramified prime. So then, after choosing certain appropriate level structure, then I have the corresponding Shimura varieties. Okay. In this situation, I can just consider its mod P fiber. of the corresponding Shimura variety, then it classifies, this is typically it's a PL type Shimura varieties. So it classifies some abelian varieties with some endomorphism, abelian threefold with the endomorphism by this quadratic imaginary field. In this case, I guess, because I consider more p fiber, I think I should do this. Plus some principal polarization and some level structure. Satisfying Cartwright's condition. Signature condition. So it's going to be some element here acts on the algebra of the abelian varieties of signature 2-1 or something like that. Okay, so it turns out after taking the p-divisible group of the abelian variety, what you get is a map from this Shimura variety to the moduli of Stukas, if you just remember the p-divisible group. Okay, so here I can consider something similar, Shimura variety, but now it's the signature 3-0 or 0-3. So it's going to be zero-dimensional Shimura variety, just a bunch of points. And it turns out what happens is you can pull back this cohomological correspondence between Stukas constructed from the geometric Satake globally to as a correspondence between two Shimura varieties. Now this is like a bicomodular surface, and this is just a bunch of points. It's zero-dimensional. But what's the correspondence here is you just consider some isogeny, A to A prime, where A is a Shimura variety here, A prime is abelian variety inside here, plus some certain condition. You can pull back. Okay, so here you have a abelian variety with endomorphisms, some like signature 2-1, but miraculously, there's some, here you have some abelian variety with endomorphism signature 3-0, but miraculously, there's an isogeny between them. So you can make such correspondence, and you can pull back the whole thing here. Okay, so what it becomes true is if you pull back this cohomological correspondence, what you get. So let me just state this. This is more p fiber, right? Everything is more p fiber. Otherwise, in characteristic 0, fiber, there won't be any correspondence between these two. But in characteristic p, there is. So, okay, so now I can try to make sense of this. So basically, let me see, how do I formulate it? So pullback of this cohomological correspondence along this map. So I get a cohomological correspondence between two Shimura varieties, and I can even take the cohomology. So then this becomes a map from the cohomology of zero-dimensional Shimura varieties, which is, because this is just a bunch of points, this is just the space of automorphic forms on some unitary group of signature 3-0. And here, this is the cohomology of a bicomodular surface. So the claim is this is the Heck equivariant. Given by. Okay, so this is still not very explicit. I can make it even more explicit as follows. By the way, this is theorem. The joint work with Liang Xiao. So let me just make even more. Let me try to make it even more explicit. So what does it mean? So what I can consider is according to the classical Satake isomorphism, more precisely, what you can do is as follows. According to the classical Satake isomorphism, first of all, the Hecke algebra at P acts on this space of automorphic forms, just explained in the first lecture, right? So according to the Satake isomorphism, you can think about this, the Hecke algebra as this adjoint invariant functions on the Langlands-Zhu group, because now the group is non-split. You need to consider not the usual conjugation, but the sigma conjugation. Okay. Now I have this. Here I have this space of G hat equivalent maps from G hat to W, which is I gave before. So this is where my sigma A live. So it turns out what happens is there exists this cycle class map, this map cohomological correspondence, in fact induces a map like that. Satisfying two conditions. So let me write it this. If I consider we get a map like that, such that how should I write it? One. Let me just like that, see like that. If you consider this cohomological, this map, and it's a dual, okay? This is going to be a map from this space to itself. I think that's not the that's not the best way to formulate it. Let me reformulate it in this way. Sorry. So I can consider this times C. Then it's going to be the map from the square of it to, let me denote this vector space by, I don't know, we might denote by W tilde. I get W tilde, tensor W tilde to H2 of this Shimura variety times H2 the Shimura variety. So a priori, this is just the cohomology with compact support, but every cycle appearing here is, in fact, in the interior, you can still take the intersection product. You get something you get sorry, I just get a little bit confused. How should I formulate? So okay, so let me just do like this. Because this is Hick equivalent, I can do this pick up any Hick finite part, pick up any corresponding part. So okay, so I get something over QL. So now I can really calculate the intersection pair, and the intersection pair is going to be given as follows. This form gives you a Satake parameter. So in particular, I have this psi A associated to the Satake parameter IF P. So this is going to be an element in the W. And in fact, psi A of the corresponding Satake parameter. This is in fact also in the representation of W. And in fact, there's up to scalar, there's a unique. So this is an element in the W, and this is in the element in the W. Up to scalar, there's in fact a unique self-intersection pairing between of G hat equivalent pairing. Okay. So at the end, what you get is the intersection pairing between those. So this cohomological correspondence, in fact, are realized by are given by, in fact, cycle class of certain algebraic cycles on the Shimura varieties. And it turns out the intersection pairing is exactly calculated by this. Right? And let me just finish by saying that all this story can be generalized to arbitrary Shimura variety as soon as there's some integral model, like what Mark constructed. So I should stop here.